How much of the universe have you really seen, not in theory, but as actual light that has hit an instrument and turned into data we can use? The short answer is almost nothing, and even the part you could ever see is smaller than you probably think. Right now, you sit inside a region of space we call your observable universe. It is a sphere centered on you, with a radius of about 46 billion light years in every direction, so a diameter of about 93 billion light years. 1 light year is how far light travels in 1 year, roughly 5.88 trillion miles, so that sphere is on the order of hundreds of sextillions of miles across, about 270 sextillion miles. That number is ridiculous, but you do not need to feel it. You just need to know this. There is a hard limit to how far light has had time to reach you since the beginning of the universe, and that limit draws a real boundary around what you can ever observe. Why are we so confident about that number? And not just guessing. Astronomers measure how fast galaxies are moving away from us by looking at their redshift, how much their light has been stretched toward the red end of the spectrum. They also have a very precise age for the universe, about 13.8 billion years. From multiple lines of evidence, especially the cosmic microwave background, plug the age, the redshift data, and the current expansion rate into our best cosmology model, and you get a distance, about 46 billion light years to the most distant regions whose light can reach you today. That gives you the size of your observable sphere. But here's the part that sounds wrong at first. If the universe is 13.8 billion years old, how can anything be 46 billion light years away? Doesn't that sound like the universe magically outran its own age? The trick is that there are two different distances involved. The time light has been traveling, and the distance right now to the object that sent it. Light from a very distant galaxy left that galaxy billions of years ago, when the universe was much smaller. That light has been traveling for 13.8 billion years to reach you. However, while the light was on the way, space itself was expanding. The galaxy did not just sit there at a fixed distance. The space between you and that galaxy kept stretching, so by the time the light shows up in your telescope, the galaxy can be tens of billions of light years away in the present. The travel time is 13.8 billion years, but the current distance can be 30, 40, even over 46 billion light years. We know this is not just a story because we see galaxies whose light is so stretched that it has moved out of visible light into infrared. The amount of stretch matches very specific expansion histories. So no, the universe is not older than 13.8 billion years, but the distances are larger than that number because the stage itself, space, has been changing while the light crossed it. Now when people say, we have seen the universe out to more than 13 billion light years, what does seen really mean? Are we talking about direct detection? Or are we mixing in things that are only inferred from models? For this, astronomers use a strict standard. Seen means light has actually hit a detector. If a telescope has recorded photons from something, and we have an image or a spectrum, then that object is directly observed. For galaxies, we have direct images out to look-back times of more than 13 billion years, that is. We see them as they were less than a billion years after the Big Bang. Beyond that, we do not have pictures. We have predictions from models. The main one is called lambda CDM, which includes dark matter and dark energy. It is adjusted to match what we do see, like galaxy clustering and the cosmic microwave background, then used to extend our expectations into regions we have no direct data from. Those regions are, in practice, known only through theory, not through actual light on a sensor. This raises the next question: is the observable universe, this 93 billion light-year wide sphere, the whole universe, or just a tiny patch? Observations say strongly that it is just a patch. When we study the cosmic microwave background, and we analyze its tiny temperature variations, we can measure the overall curvature of space on very large scales. The answer we get is space is extremely close to flat in the part we can see, not strongly curved like the surface of a small sphere. If the universe were small and closed, like the surface of a ball, that curvature would show up clearly. Because it does not, the simplest conclusion is that the universe extends far beyond our observable region, at least hundreds of times farther in radius, and it might be infinite. Whatever the exact answer, we only have photons from a limited region around us. Everything beyond that might as well be behind a permanent curtain. And this is where volume completely destroys your intuition. If the whole universe has a radius that is, say, 250 times larger than the radius of your observable region, that does not sound extreme. It is just a couple hundred times bigger in each direction. But volume grows with the cube of the radius, because space has 3 dimensions. So 250 times the radius means 250 times 250 times 250 in volume, which is about 15.5 million times more volume. That would make your observable universe less than 1/15 millionth of the total, safely below 1 in a million. And remember, 250 times the radius is a conservative example, not a hard upper limit. So already, before you even talk about telescopes and surveys, how much of the universe have we seen has two huge cuts. First, you are limited to the observable region, which is probably far less than 1 millionth of the total volume. Second, even inside that region, only a small subset is directly observed, and an even smaller subset is studied in any real depth. Which leads to the next, sharper question. Inside this already limited observable sphere, how much have you actually looked at with serious detail? Not just, there is a fuzzy object there, but we have deep images, spectra, distances, and structure. When you hear about famous deep fields and beautiful galaxy maps, it sounds like we have covered the sky pretty well, but we have not. The true fraction is tiny. And once you realize that most of the full universe is outside your observable region, and most of your observable region has barely been scanned, a more uncomfortable idea appears. Maybe the universe you think you know, from popular images and maps, is based on a very small sample, a tiny patch of sky examined in high detail, and some well-measured slices spread across the rest. So the next step is obvious. If your observable region is this huge, and your instruments are this limited, how much of the sky have your best telescopes actually covered deeply? How much of that 46 billion light-year radius sphere has been mapped with real care? And how much of it is still just numbers in a model rather than light in a camera? What if I told you that almost every famous deep space image you know comes from a patch of sky, smaller than a grain of sand held at arm's length? Would you still feel like we've mapped the universe? Because once you put real numbers on what our telescopes have actually covered, the answer is brutal. We've barely started. Take the Hubble Deep Field. Astronomers pointed the Hubble Space Telescope at what looked like a blank, boring patch of sky and stared at it for days. If you hold a grain of sand at arm's length, the area that grain covers on the sky is roughly the size of that original deep field. In that tiny patch, Hubble found about 3,000 galaxies, not stars, entire galaxies, each one with hundreds of billions of stars of its own. Now scale that up. The sky is covered in those little sand grain patches. Multiply those 3,000 galaxies by all the patches needed to cover the full sky, and you are already talking about hundreds of billions of galaxies, easily. And remember, that is just what shows up at the depth Hubble could reach in that one small stare, not what's hiding even fainter. So here's the key question. If one microscopic patch of sky is that crowded, how much of the sky have we actually looked at with that kind of insane depth? The whole sky is about 41,253 square degrees. That is the total area you could, in principle, map. All of the truly deep survey fields combined, the Hubble Deep Field, the Ultra Deep Field, GOODS, the newer JWST deep fields. Together, they cover far less than a single square degree. You are not missing a digit there. It is less than 1 square degree out of over 40,000. That means the fraction of the sky we've imaged that deeply is on the order of a few 10,000ths, a few parts in 10,000. For the rest of the sky, we either have shallower images or in many wavelengths, almost nothing. And just when that sinks in, here comes another question. If our deep coverage is that tiny, how far back in time have we actually managed to see, even inside those postage stamp regions? That is where JWST comes in. The James Webb Space Telescope is tuned for infrared, which is exactly what you need when the light from very distant galaxies has been stretched by cosmic expansion. Webb has already found candidate galaxies with redshifts above 13. In simple terms, that means we are seeing them as they were when the universe was probably under 400 million years old, less than 3% of its current age. These are not guesses, these are real detections, where the light has been broken into its colors and checked. But again, they come from very small areas, narrow fields on the sky. We are pushing the frontier of what we've actually seen closer to the Big Bang, but only along a few very thin sightlines. So now you have two extremes, ultra-deep, ultra-narrow views on one side and the rest of the sky, which can't all be done at that depth. That raises a trade-off you almost never think about when you look at pretty images online. Do you go deep or do you go wide? Deep surveys, like the Hubble Deep Fields and JWST's deep pointings, are like drilling a very thin core straight down. You see incredibly far, but in a tiny angular area. Wide surveys try the opposite approach. The Sloan Digital Sky Survey, SDSS, has mapped millions of galaxies over about 1/3 of the sky, with a big ground-based telescope and a dedicated camera. It has given us a three-dimensional map of nearby cosmic structure, but nearby here means out to only a few billion light-years in good detail. The upcoming Vera Rubin Observatory, with its Legacy Survey of Space and Time, LSST, will repeatedly scan large parts of the sky, catching changes and building a deep, wide image over time. Wide surveys give you many objects and motion, but not the same extreme depth as a Hubble or JWST deep field. Deep means you see very far, but only in narrow beams. Wide means you see a lot of the sky, but not as faint and not as far back in time. This leads to the next uncomfortable number. Out of all the galaxies that could, in principle, be inside your observable universe, how many have we actually cataloged in any detail? Current catalogs from surveys like SDSS, Pan-STARRS, DES, and others list on the order of hundreds of millions of galaxies with measured positions and tens of millions with detailed spectra, where we know their distances and some of their physical properties. That sounds huge until you compare it to how many galaxies we think are really out there. Estimates based on Hubble and JWST deep data suggest the observable universe may contain something like 1 trillion or more galaxies in total. If there are 1 trillion galaxies, and you have catalogs for maybe a few 100 million, then on a good day you have rough data for less than 1 in 1,000 and detailed three-dimensional information for less than 1 in 10,000. In other words, when it comes to galaxies, the share you've truly seen and measured is well below 0.1%. And that's just counting galaxies as single dots on a map, not all the internal structure, stars, planets, gas, and black holes inside them. If you zoom in further, the fraction you know anything about in detail drops towards zero, so fast it is basically gone. We live in a universe that looks full of data in press releases and wallpapers, but statistically, our sample is tiny. So here's the twist that pushes the tension even higher. even in the parts of the sky where we have looked, and even for the galaxies we have catalogued. The universe is not sitting still and waiting for us to finish the survey. It is expanding, and that expansion is stretching the light from those galaxies as it travels. Some regions are already receding so fast that their light is being stretched out of the wavelengths we can easily detect, and some are on track to become effectively invisible to us in the future. If just mapping a thin slice of your observable universe is already this hard, what happens when the universe itself keeps pulling more and more of that slice out of reach? How do you even talk about seeing the universe when the thing you are trying to see is literally running away from you, faster and faster as time goes on? If light is the fastest thing in the universe, why is most of the universe permanently off limits to you, even if you had infinite time and perfect technology? This is the part almost nobody tells you clearly. The problem isn't your telescopes, it's the rules of space and time themselves. Start with the basic number you've heard a million times. Light travels about 186,000 miles per second. That sounds unbeatable. In 1 second, light goes around Earth more than 7 times. In 1 year, that speed gives you 1 light year, about 5.88 trillion miles. Now stack that up against your observable universe, which has a radius of about 46 billion light years. Even if the universe stopped expanding and froze in place, light would need 46 billion years just to cross from one side of your observable radius to your position, and another 46 billion to go all the way across the diameter. That already dwarfs the current age of the universe, 13.8 billion years. But the universe is not static, it's expanding, and that changes everything. When we say expanding, we don't mean galaxies shooting through space like bullets. We mean space itself is stretching, so the distances between galaxies grow over time. Because of that, there are regions far enough away that their distance from you increases faster than light can cover it. That does not break relativity, because nothing is moving through space faster than light. The space in between is just getting bigger. The result is brutal. Some regions are already so far and receding so fast that no signal sent from them now will ever reach you. Not in 10 billion years, not in a trillion. So how do we even measure this expansion? And how do we know how fast things are receding if we can't fly out there and check? That's where redshift comes in. Think of redshift as your cosmic speedometer. When a galaxy is moving away from you, the light waves it sends get stretched, their wavelength gets longer, they shift toward the red side of the spectrum. Astronomers measure this stretch by looking at very specific fingerprints in the light, lines from hydrogen, helium, oxygen, and other elements. We know exactly where those lines should be if the source is at rest. When we see them shifted to longer wavelengths, we can calculate how much the universe has expanded while that light was traveling. If we say a galaxy has redshift about 1, that means the universe was roughly half its current size when that light left. You are seeing it about halfway back in cosmic history. When we see galaxies with redshift greater than 7, 10, 13, we are seeing them as they were when the universe was less than a billion years old. Those numbers are not just labels, they come directly from spectra, from tracking how much those chemical fingerprints have moved. Now, to really feel how quickly expansion wins, it helps to put the Hubble constant into units that don't sound like a physics paper. The Hubble constant is the number that tells you how fast galaxies recede as a function of their distance. In everyday terms, it's about 44 miles per second for every million light years of distance. So if a galaxy is 1 million light years away, on average it's receding at around 44 miles per second. If it's 10 million light years away, the recession speed is about 440 miles per second. Push that farther. At a billion light years, you're talking tens of thousands of miles per second. At several billion light years, the recession speed can approach or exceed the speed of light, not because the galaxy is breaking the rules, but because that 44 miles per second per million light years piles up over huge distances as space stretches. At around 10 billion light years or more, you get into regimes where, in the standard model, the recession speed can beat light. That means the gap is growing faster than light can close it. This leads directly to two hard boundaries that limit what you can ever see or influence, no matter what you do. The first is the particle horizon. That's basically the distance out to which light has had time to reach us since the Big Bang. Right now, that's about 46 billion light years in radius. Anything beyond that, if it sent out light in the past, that light has not reached us yet. The second is the event horizon. That is even worse. The event horizon is the maximum distance from which light emitted today, right now, can ever reach us in the future. Because of dark energy and accelerated expansion, that radius is smaller than the particle horizon. Calculations in standard cosmology show that even as time goes to infinity, the largest moving distance that can ever send us a new signal is on the order of about 60 billion light years. Everything beyond that distance is already lost in a permanent sense. Any light it emits now, or in the future, will never get here. So you end up with a strange picture. There are parts of your observable universe that you can see today, because light left them billions of years ago when they were closer, but if they send out light now, it will never reach you. You see their ancient past, but you are forever cut off from their present and their future. And beyond that 60 billion light-year limit, even ancient light will never make it at all. Those regions might exist, might be full of galaxies, stars, maybe life, but no photon from those zones will ever hit a detector in our part of space. Then, a bigger question shows up. If most of space is forever invisible, how can we say anything at all about it without just making things up? This is where the difference between observation and inference becomes critical. The slice of the universe we can see follows very simple, consistent rules. The way galaxies cluster, the patterns in the cosmic microwave background, and the brightness of distant supernovae all fit the same expanding universe model, with dark matter and dark energy. Because this model works across huge ranges of distance and time in the region we can observe, we assume, as a working rule, that the same physics continues beyond our horizon. That's an assumption, but it's the simplest one that matches the data. What we do not have and never will have is direct confirmation from photons coming from those unreachable regions. They are outside both our current observable sphere and our future event horizon. We can simulate them, we can predict what should be there, but we cannot observe them. Our universe, in the strict, data-only sense, is permanently limited to a finite volume. And just when you think, okay, fine, but at least we can keep pushing back closer and closer to the Big Bang inside that volume, you hit one more hard stop that you cannot cross, even in principle. There is a literal wall of light in your way. The earliest possible photo of the universe, beyond which normal light simply cannot show you anything. So what is that wall? Why does it exist? And how can we claim we've seen the whole sky at that depth, but only at one very specific moment in cosmic history? What if I told you there is a hard wall in front of you in time, a surface you can see but never look beyond with normal light, no matter how good your telescopes get? That wall is real, and you are already staring at it. It's called the cosmic microwave background. Right now, all around you, there is a faint glow of microwave radiation coming from every direction in the sky. If your eyes could see microwaves, the whole sky would look like a smooth, dim fog. That glow is the afterglow of the early universe, called the CMB. It was emitted when the universe was only about 380,000 years old. Compare that to today, about 13.8 billion years old. You're looking at a snapshot from when the universe was a tiny fraction of its current age. The temperature of this glow is about 2.7 Kelvin. which is roughly minus 454.8 degrees Fahrenheit, just a few degrees above absolute zero. Satellites like COBE, WMAP, and Planck have mapped this radiation with extremely high precision. They've measured not just the average temperature, but tiny variations across the entire sky. So why is this glow there at all? And why does it come from that specific early time, a few 100,000 years after the Big Bang, and not earlier? Before that point, the universe was in a very different state. It was much hotter and denser, filled with a plasma, a mix of protons, electrons, and photons, constantly smashing into each other. In that plasma, light could not travel freely. Photons were scattered over and over again by the charged particles. The whole universe was like the inside of a star, bright, hot, and completely opaque. As the universe expanded, it cooled. When the temperature dropped to around 3000 Kelvin, which is around 5500 degrees Fahrenheit, something important happened. Protons and electrons could finally combine to form neutral hydrogen atoms. Once that happened, there were far fewer free electrons around to scatter light. The universe went from opaque to transparent in a relatively short time. Photons that had been trapped in the plasma were suddenly free to travel in straight lines. Those are the photons we see today as the CMB. This process is called decoupling or recombination. Before that, there is no older image in light to capture because light simply couldn't escape. That's why you cannot see farther back in time with normal light than about 380,000 years after the Big Bang. There is no earlier light-based picture to take. But the CMB is not perfectly smooth. When you look at detailed maps from Planck, you see tiny temperature ripples, hot and cold spots, at a level of about 1 part in 100,000. That sounds almost perfectly uniform, but those tiny differences matter. Slightly hotter spots correspond to areas that were a little less dense, slightly cooler spots to areas that were a little more dense. Over billions of years, gravity amplifies those small differences. The slightly denser regions pull in more matter, grow, and eventually become the large-scale structures we see today: galaxy clusters, filaments, and voids. So when you look at a map of the CMB, you are not just seeing a random pattern. You are looking at the seeds of the present-day cosmic web. It is direct observational evidence that the structure you see around you now traces back to very specific initial conditions. Here is one thing that makes the CMB different from almost everything else we've talked about so far. We have mapped it over essentially the whole sky. Galaxy surveys are always partial. They cover some fraction of the sky to some depth in some wavelength. The CMB, though, has been observed across almost 100% of the sky. That means, at this particular early moment, around 380,000 years after the Big Bang, you have a full sky view. In that sense, you really have seen your entire observable universe, but only at that single early time, and only in a very blurry way. The resolution is low. Each pixel in a CMB map is huge, often corresponding to regions tens of millions of light years across. There are no individual galaxies, no stars, no planets, just large patches of slightly different temperature. Now, how far back in expansion terms is this surface really? When cosmologists talk about the CMB, they often quote a redshift of about 1100. That means that, since that light was emitted, the universe has stretched so much that the wavelengths of those photons have been lengthened by a factor of roughly 1100. What started out as visible or infrared light at a few thousand degrees has been stretched all the way into microwaves at just a few degrees above absolute zero. That redshift value doesn't come out of nowhere. It comes from fitting the CMB spectrum very precisely and tying it together with other data, like the pattern of galaxy clustering, baryon acoustic oscillations, and the brightness of distant supernovae. All of those pieces line up and point to the same story. The CMB is light from when the universe was at redshift around 1100 and about 380,000 years old. Everything before that, earlier than the CMB, is in a different category. We cannot see it with ordinary light at all. If we want to probe earlier times, we have to use different messengers, like relic neutrinos from the early universe, or primordial gravitational waves. Or we have to rely on theoretical models tested indirectly by later observations. We do not yet have a full sky map of these non-light signals. We barely have the first hints of gravitational waves, and we have not directly detected the predicted cosmic neutrino background. That means that for the deepest, earliest times, our picture is still incomplete and very model-dependent. So at this point, you have hit a hard limit with light. There is a literal wall in time, at about 380,000 years after the Big Bang, beyond which photons cannot tell you anything directly. From here on, if you want to see deeper into the universe's past, or uncover the bulk of its contents, you need new senses that are not based on ordinary light at all. The obvious question is, if light can only show you 5% of the universe's content, and only back to a certain time, what about the rest? How do you study the invisible matter and energy that you know must be there but never see? And what does that do to your answer to the question, how much of the universe have we actually seen? What if I told you that even in the parts of the universe you can actually see, the galaxies you have sharp photos of, more than 90% of what's really there never shows up in the image at all? You are not just blind beyond your horizon, you are mostly blind inside it too. And the only reason you know that is because gravity keeps outing the invisible stuff. Start with one of the cleanest clues: how fast stars move in galaxies. In a simple world, the farther you go from the center of a galaxy, the slower stars should orbit, because most of the visible mass is toward the middle. If you're far out in the disk, the pull should get weaker, and your orbital speed should drop. That's what you see in the solar system. Planets farther from the sun move slower. But when Vera Rubin and others measured how stars actually rotate in galaxy disks, including in the Milky Way, that's not what they found. Stars tens of thousands of light years from the center still move at roughly the same speed as stars much closer in. In the Milky Way, that's around 130 to 150 miles per second. Even out in the outer disk where there isn't much visible gas or starlight. The rotation curve, the graph of speed versus distance from the center, stays almost flat instead of dropping. If you try to explain that with only the stars and gas you can see, the gravity just isn't strong enough to hold those fast-moving outer stars in orbit, the galaxy should fly apart. The only way to fix this without breaking basic physics is to add a lot of extra matter that doesn't glow, forming a huge extended halo around the visible galaxy. That unseen component is what we call dark matter. You don't see it directly, but you see its fingerprints in the motion of stars. You could still say, okay, maybe that's just a sign that we're using the wrong gravity formula. Maybe there isn't extra matter. Maybe the law is different at low acceleration. That argument floated around for a while, but then you get hit with a much sharper piece of evidence, a case where normal matter and total mass clearly separate in space, and gravity follows the total, not just the glowing part. That is the bullet cluster. The bullet cluster is a system where two big galaxy clusters have collided. When they crashed through each other, the hot gas in each cluster, which you can see in X-rays, slammed together and slowed down because of drag. The galaxies themselves mostly pass through, because they're relatively sparse, and so did the dark matter, if it exists, because it doesn't interact much except through gravity. Now, if you map where the X-ray gas is, you get one picture. If you map where the gravity is, using gravitational lensing, how the cluster bends and distorts background galaxies, you get another. The result, most of the mass is not where most of the glowing gas is. It's offset, aligned with the galaxies that pass through. That tells you something huge. The bulk of the matter in those clusters does not behave like normal gas. It barely collides at all. It only shows up through its gravity. That's very hard to explain by just tweaking the gravity law. It strongly points to a real invisible component, dark matter. So that's the matter side. But the expansion of the universe itself also refuses to behave the way you'd expect from just normal and dark matter. For most of the 20th century, astronomers assumed the universe's expansion should be slowing down over time because gravity from all the matter inside it pulls inward. To test that, they used type Ia supernova, explosions of white dwarf stars, as standard candles. These supernovae have nearly the same intrinsic brightness, so if one looks dimmer than expected for its redshift, it means it's farther away than a simple, slowing expansion model predicts. In the late 1990s, two independent teams measured dozens of these supernovae at large distances. The result shocked everyone. The supernovae were too dim, consistently. That meant they were farther away than they should be if the universe's expansion had been slowing down. The only way to make sense of the data was to accept that the expansion is not just continuing, it's speeding up. Something is pushing on space itself, making the rate of expansion increase with time. We call that something dark energy. Again, you don't see it directly, it doesn't come as photons, but its effects show up clearly in how distances and redshifts relate. When you combine all of this, you get a very lopsided breakdown of what the universe is made of. Roughly 5% is ordinary matter, atoms, the stuff that makes stars, gas, planets, people, everything you can see and touch. Around 25% is dark matter, which only shows up through gravity and maybe very weak interactions, but does not emit or absorb light. And about 70% is dark energy, a form of energy tied to space itself that drives the accelerated expansion. Those numbers come from three independent observational pillars: the detailed pattern of the cosmic microwave background, the way galaxies cluster on large scales, and the supernova data on expansion history. They all point to the same rough 5/25/70th split. So even inside the part of the universe you can see with light, more than 90% of what exists is invisible in any normal sense. That means when you look at a galaxy photo, you are really seeing the frosting, not the cake. The visible stars and gas are just the thin, bright layer on top of a huge dark matter halo, all inside a universe whose expansion is dominated by dark energy. But you're not helpless in the face of that invisibility. You have one powerful tool that lets you map where mass is, even if that mass never sends you a single photon: gravitational lensing. Gravity bends light. When light from a distant galaxy passes near a massive object, like a cluster, its path gets warped. If the mass distribution is big and dense enough, you can get stretched arcs, multiple images, and ring-like shapes. That's called strong lensing. Even when the effect is small, you can measure tiny systematic distortions in the shapes of many background galaxies. That's weak lensing. By analyzing these distortions, Hubble and big ground-based surveys can reconstruct maps of where the mass actually is, regardless of whether it glows. Programs like CLASH and the Hubble Frontier Fields have done exactly this, turning images full of arcs and smears into detailed mass maps. Those maps show clumps and halos of matter that do not match the distribution of visible light. That's dark matter, directly traced by how it warps space. No photons come from the dark matter itself, but the way it bends other photons gives away its position and its density. Put all that together and you get a pretty harsh answer to our main question so far. Even in regions where you think you've seen the universe in detail, beautiful Hubble shots, precise spectra, CMB maps, Most of the actual content is either dark matter or dark energy. You are building your entire picture of the universe on a thin layer of visible matter, plus indirect signals from gravity and expansion. The phrase, "we've seen the universe," becomes very misleading, very fast. And we're still talking about big average quantities, total mass, overall composition, large-scale structure. We haven't even started counting the individual pieces, the stars, the planets, the black holes, the smaller objects that actually make up that 5% of normal matter you can in principle study directly. When you zoom down from "what is the universe made of" to "how much of the fine detail have we actually mapped," the fraction you truly know drops from tiny to effectively zero. So the next hard question is this. If more than 90% of the universe's content is invisible, and even the remaining 5% is made of objects you mostly haven't measured, what does our seen universe really mean at the level of individual stars, planets, and violent events like black hole mergers? How detailed is the map you're actually working with? You might be thinking, okay, sure, we're blind to most of the universe, but at least we've nailed our own galaxy, right? No, not even close. When you zoom in from the big picture to the fine detail, the amount we've actually mapped becomes almost nothing. Take just our own home galaxy, the Milky Way. Estimates put it somewhere between about 100 and 400 billion stars. The Gaia spacecraft has done an insanely detailed job by human standards. It has measured precise positions and motions for over a billion stars. That's incredible data. But step back and look at the percentage. A billion out of hundreds of billions is under 1%. That means more than 99% of the stars in just our own galaxy still don't have precise Gaia-level measurements. And that's before you even touch other galaxies. Now scale up. There may be a trillion or more galaxies in the observable universe, each one with billions or hundreds of billions of stars. The total number of stars is mind-blowing, on the order of 10 to the 22, 10 to the 24, somewhere in that range. Against that number, the fraction of stars whose light we've individually resolved and whose properties we've measured in real detail rounds to zero. Not small, zero for all practical purposes. You live in a universe that is full of stars, and you've looked closely at a tiny sliver of one galaxy's worth. And that's just stars. What about planets, the things we really care about when we talk about life and habitability? As of now, astronomers have confirmed only a few thousand exoplanets, planets around other stars. We spot them using methods like transits, where a planet passes in front of its star and causes a tiny dip in brightness, and radial velocity, where a star wobbles at a speed of just a few feet per second because of the planet's pull. We've directly imaged only a few dozen exoplanets, big and young ones that glow in infrared and are far from their host stars. But if you guess just a few planets per star, across all galaxies, you get ridiculous totals, nonillions of planets, numbers with more zeros than you'll ever want to write. Against that, a few thousand confirmed planets is nothing. Almost all possible worlds in the universe are completely unknown to you. You've seen their category in theory, but you haven't seen them as actual worlds, with measured orbits, atmospheres, or surfaces. Even when we pull back up a level and look at galaxies instead of stars and planets, the map is still low resolution. Surveys like the Sloan Digital Sky Survey have built three-dimensional maps of millions of galaxies. They do this by taking images, measuring redshifts to get distances, and plotting where the galaxies sit in space. When you look at the result, you see a structure we call the cosmic web. Filaments of galaxies and big empty voids stretching for hundreds of millions of light years. It's impressive, it's real, and it shows that matter on large scales isn't randomly spread out. But those maps are mostly complete only out to a few billion light years. Beyond that, the coverage drops off. You're limited to the brightest galaxies and rare objects like quasars. The web gets fuzzier, the gaps get bigger, and your map of the universe starts turning into a few sampled slices instead of a full volume. For most of the observable universe, we do not have a dense 3D galaxy map. We have thin traces. In the last decade, you opened one brand new way to sense the universe, and it's easy to overhype what it can do. Gravitational waves. Detectors like LIGO and Virgo have recorded dozens of mergers of black holes and neutron stars, events happening hundreds of millions to billions of light years away. Each detection contains information about the masses of the objects, how fast they spiraled together, and an approximate distance. That's amazing. It's a completely different channel of information, not based on light at all. But there's a catch. The angular resolution, the ability to pinpoint where on the sky the signal came from, is bad. A gravitational wave event might be localized to a patch of sky that's dozens or even hundreds of times bigger than the full moon. You know, something merged somewhere in that area, but you don't get a high-resolution image. So yes, you've opened a new eye, but right now it sketches a very rough outline. It does not give you a sharp map yet. Then, there's multi-messenger astronomy, where you catch the same event in several channels at once. The best example so far is the neutron star merger detected in 2017 called GWW 170817. LIGO and Virgo picked up the gravitational waves. Space telescopes saw a burst of gamma rays. X-ray, visible light, and radio telescopes all followed up. This one event, about 130 million light-years away, gave us a detailed look at what happens when two neutron stars collide, including strong evidence that heavy elements like gold and platinum are made in these mergers. But here's the problem. Events like that are rare in our data. We've only seen a handful of true multi-messenger detections so far, compared to the countless mergers that must have happened and are happening across the universe. You got one very detailed story, and a small sample of others, out of an enormous, mostly unseen population. So if you step back and ask, how detailed is our map of the universe really? The answer is harsh. For stars, we have precision data for a tiny fraction of our own galaxy, and effectively 0% of all stars overall. For planets, we've confirmed a few thousand out of a possible non-alien scale population. For galaxies, we have good 3D maps in a limited volume and patchy coverage beyond that. For violent events, like black hole and neutron star mergers, we've just opened our eyes and seen the first few dozen. And while you're slowly filling in these tiny pieces, there's another problem you can't ignore. The universe is not politely waiting while you map it. Because of dark energy and accelerated expansion, many of the galaxies you can see now are already on track to slip beyond any possible communication. Their light is stretching, their signals are fading, and over long enough timescales, they will become effectively invisible to any future observer. So you're in a strange position. You've seen almost nothing, you've mapped almost nothing in detail, and at the same time, the window that lets you see this almost nothing is shrinking for huge parts of the universe. Which raises the next, more unsettling question. What happens to your picture of the universe when the galaxies you rely on to build it start disappearing from view forever? Right now, you can see galaxies that, in a very real sense, are already gone to you, not because they exploded, but because the universe has pushed them past a point of no return. You're watching their old light. But anything they do now, any signal they send today, will never reach you, ever. This happens because the expansion of the universe isn't just continuing, it's accelerating. Dark energy, that's 70% of the universe's energy budget, acts like a built-in push on space itself. The evidence for this is not vague. Those type Ia supernova measurements from the 1990s showed that distant supernovae are dimmer than they'd be in a slowing universe. The patterns in the cosmic microwave background agree. Independent data sets, different methods, same conclusion. Expansion is speeding up. When expansion accelerates, there's a critical distance where things cross a line. Beyond that distance, the space between you and a galaxy is expanding so fast that any light it emits now gets dragged away faster than it can close the gap. That light never makes it to you. So some galaxies you see in your telescope right now, whose ancient light is just arriving, are already beyond that line in the present. Their current state is causally disconnected from you. For all practical purposes, you will never know what they look like now. To make this more precise, you need to separate two very different horizons. First, the particle horizon. That's the boundary of your observable universe, the maximum distance from which light has had time to reach you since the Big Bang. Today, that's about 46 billion light years in radius. Everything you see in any direction sits somewhere inside that sphere, as it was in the past. Second, the event horizon. That's the maximum distance from which light emitted today can ever reach you in the future. Because dark energy is driving accelerated expansion, that radius is smaller than the particle horizon. Calculations using the measured dark energy density give a communication limit of roughly 16 to 18 billion light-years in present-day distance. Anything farther away than that, right now, can send out all the light or radio signals it wants, and none of it will ever get here. Light that is already on the way, emitted billions of years ago, can still arrive from beyond that distance, but no new information from those regions will ever show up. So your situation is weird. You can currently see some galaxies that are more than 18 billion light-years away in present distance because you're seeing light they emitted long ago, when they were closer. But you cannot get any new updates from them. No message you send will ever reach them, and no light they emit today will ever reach you. They are in your visible past, but outside your future communication zone. Now push the clock forward, way forward. Simulations that use our current measurements of dark energy and matter show what happens over tens to hundreds of billions of years. As expansion keeps accelerating, light from distant galaxies gets stretched to longer and longer wavelengths. Their light shifts out of the visible, then out of infrared, and eventually out of any realistic detection window. In that far future, almost all galaxies outside the local group will have redshifted so much that they'll fade below detectability. What's left in the night sky then? Basically just your local neighborhood, the Milky Way and Andromeda, which by then will have merged into a single large galaxy, plus a few smaller companion galaxies bound to them. The rest of the universe will not just be dark, it will be physically unreachable and invisible. Future astronomers, even with absurdly advanced telescopes, will not see a universe full of galaxies receding from them. They will see one big galaxy, a few small ones, and nothing else. That creates a strange kind of cosmic archaeology problem. Right now, in this era, you can still detect the cosmic microwave background. You can see countless external galaxies. You can watch expansion in action. From that, you can reconstruct a Big Bang, measure dark matter and dark energy, and build a full cosmology. But a civilization living hundreds of billions of years from now will not have that evidence. No CMB they can easily detect, no distant galaxies tracing a Hubble-like expansion, no large-scale structure map beyond their local group. With only their single merged galaxy to study, the idea of an expanding universe with a hot beginning will be extremely hard to uncover from direct data. We live at a special time, not in the philosophical sense, but in a technical, observational sense. The key signals that reveal the universe's history and composition are still accessible, but they will not stay that way forever. The universe is actively erasing the evidence stretching it, dimming it, and pushing it out of view. And here's the kicker. This isn't just a for now limitation you can beat with patience and better tech. Based on the measured value of dark energy and how well it fits the CMB and supernova data, you can already say something absolute. Most of the total volume of the universe is permanently out of reach. Not just hard to see, not just currently beyond our instruments, but fundamentally unreachable in principle. Even if you had infinite time and perfect detectors, you would never collect light or send a signal to the majority of regions that exist. The equations governing expansion simply do not allow it. So when you ask, how much of the universe have we seen? The honest answer has two cuts. First, the part you could ever exchange information with is only a fraction of your current observable sphere. Second, your observable sphere is almost certainly a tiny fraction of the total universe, maybe far less than 1 in a million of the total volume. Put together, most of what exists is not just unseen today, it is guaranteed to remain unseen forever. Which brings us to the last direct question you can't dodge anymore if you add up everything: the sky coverage, the galaxies counted, the stars and planets measured, the dark components inferred, and the hard limits from expansion. What fraction of the universe have you actually seen right now with real instruments and real data? And how close is that number to just being essentially zero? So after all this, what's the actual score if you force yourself to put numbers on how much of the universe you've really seen right now with real instruments, not theories or simulations? Let's go piece by piece, and you'll see how fast the number drops toward basically nothing. Start with the sky itself. In terms of area, big surveys like SDSS and others have imaged a large fraction of the sky at moderate depth. That sounds good, but that's not the kind of data people show when they say, we're looking back to near the beginning of time. For true deep Hubble or JWST level views, the kind that pick up tiny, faint galaxies more than 10 billion light years away, your coverage is microscopic. All the classic deep fields and ultra-deep fields, plus the new JWST deep pointings, add up to well under 1/100th of 1% of the sky. In other words, for high-resolution edge-of-time imaging, you've stared deeply at far less than 0.01% of the full dome above you. The rest, in that sense, is either shallow or not mapped at all in those wavelengths. For the deepest views, you have a literal speck. Now look at galaxies. Across all surveys, you've cataloged on the order of hundreds of millions of galaxies. For tens of millions of those, you've measured distances and basic properties using spectra. That's a real, solid data set. But all the evidence from Hubble and JWST deep fields points to the observable universe containing something like 1 trillion or more galaxies in total. Compare those two numbers. If there are 1 trillion galaxies and you've got rough data on a few hundred million, you're below 1 in 1,000 in terms of we know where it is and roughly how far it is. If you restrict to galaxies with detailed three-dimensional information, you drop to under 1 in 10,000. And that's inside just the observable universe, not counting anything beyond your horizon. Next, stars and planets, which is where people instinctively care the most. Using galaxy counts and typical numbers of stars per galaxy, the total number of stars in the observable universe is estimated at around 10 to the 22 to 10 to the 24. That's a 1 followed by 22 to 24 zeros. Against that, the number of stars for which we have really detailed individual measurements is tiny. Gaia gives you exquisite data for over 1 billion stars in the Milky Way. A few other missions and ground-based surveys add more, but all of that still covers far, far less than 1% of just our galaxy, and a completely negligible fraction of all stars everywhere. If you tried to compute the fraction of all stars whose properties we've measured in any serious way, The answer is so small that for any practical conversation, it rounds straight to zero. For planets, it is even more extreme. You have a few thousand confirmed exoplanets, plus a larger pool of candidates. Simple estimates, a few planets per star on average, push the total possible planets in the observable universe up around 10 to the 24 or more. So you're at thousands known versus nonillions that probably exist. That is not a survey, that's a tiny sample. Zoom back out to the composition of the universe as a whole. From the CMB, galaxy clustering, and supernova observations, you get that rough 5/25/70th split, about 5% normal matter atoms, about 25% dark matter, about 70% dark energy. That breakdown is not wild guesswork. It's locked in by multiple independent datasets that all agree. But even that 5% of normal matter is not something you see completely. You get detailed spectra for a small subset of it, mainly stars and gas in nearby or bright galaxies. The vast majority of that 5% shows up as unresolved light, or as gas inferred from indirect signatures. The other 95%, the dark matter and dark energy, never sends you photons directly. You only know it is there because of its gravitational effects and how it changes the expansion history. So most of the universe's content is not seen, it's inferred. You are building your picture of reality on a thin slice of that 5%, and on patterns and wobbles that hint at the other 95. Now put all this inside the spatial limits you already know. Your observable universe is a sphere with a radius of about 46 billion light-years. There is strong evidence that the whole universe is much larger than that. If the actual radius of the universe is even just a few hundred times bigger than the radius you can see, the volume difference explodes. Volume scales with the cube of the radius, so a few hundred times the radius means millions to tens of millions of times the volume. That puts your observable bubble at less than 1/1,000,000th of the total, maybe far less, depending on the true size. And that's the optimistic case, where the universe is only a few hundred times bigger in radius, not infinite. Inside that already tiny bubble, your detailed observational coverage is another tiny fraction. You have deep, high-resolution imaging over less than 0.01% of the sky. You have good 3D galaxy maps out to only a small part of the radius. You have precise stellar data for under 1% of one galaxy. You have confirmed a few thousand planets out of a possible 10 to the 24 or more. If you tried to combine all those fractions into a single number for what fraction of the universe's volume has been surveyed in high detail across time, objects, and wavelengths, you end up way below 1 in a billion, probably way lower than that. It's so small that calling it almost nothing is not drama, it's just arithmetic. And yet here's the twist you can't ignore. With that almost nothing slice of data, you've already rewritten your idea of reality. From a handful of tiny deep fields, a few million spectra, a sky-filling microwave glow at 2.7 Kelvin, and a few dozen gravitational wave detections. You've learned that space is expanding, that time had a hot, dense beginning, that about 95% of the universe is made of dark matter and dark energy you can't see directly, and that most of the universe will always be beyond your reach, no matter how long you wait or how good your technology gets. So when someone asks, how much of the universe have we actually seen? The honest answer is this: almost none of it. A microscopic fraction of the volume, a tiny fraction of the galaxies, effectively 0% of the stars and planets, and direct access to only 5% of the total cosmic budget. But that vanishingly small slice has been enough to show you that the universe is bigger, older, stranger, and more locked off than anyone guessed a century ago. And that's why every new photon that hits a detector Every new spectrum, every new gravitational wave signal matters so much because when you've seen this little, almost any new piece of data has a real chance to change the story. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.